Hi everybody, my name is Petru Lauric and I work for Freescale. We happen to be a partner of ARM, so it's good timing. The order of the presentations is great. Um, what I will talk about today is an introduction to the topic of a different type of tracing that some of you may not be familiar with, and that is tracing that is focused on the needs of the systems which process networking data. I'll talk a bit about the type of trace data and the type of performance analysis tools that we have developed at Freescale, and about how some of the requirements that we have, we think will apply to the Linux community. These are the main topics that I want to talk about today. I'll talk a bit about what is a network processor and about why we want to analyze it in a way that's different from a generic Linux system. I want to talk a bit about the hardware trace support that is sometimes necessary to analyze these network processors. I'll talk about the software trace and how we are going to model and visualize this data that we're going to get from all these various sources. And if we have time at the end of the demo, at the end of the presentation, I'll try to do a quick demo of the tool that we have today. So in a nutshell, a network processor is a device that has been designed to process network packets. You'll find these things in routers, in base stations, on the cell phone towers, and so forth. And what these things typically include is their SoCs, their systems on chips, and they include a set of general purpose cores, and also they have some specialized hardware that is used to offload some of the networking tasks from software to hardware. And I'll talk a bit about how one such network processor architecture looks like to support the explanation of the concepts that I'm going to present. Okay, so the question is, why do we have to analyze things in terms of network packets? And on this slide, I try to outline the main reasons why we want to do that. The problem is that the software analysis tools that exist today, such as the software debuggers, the profilers, and the tracers that we have talked about today, they don't know, they're not aware of the network packets. They're agnostic to that. And to a large extent, the same thing happens with the hardware-based tools. The hardware designers, they can design performance counters in the system. They can give you all kinds of hardware trace data. But again, those things are not going to be closely correlated with the networking data that flows through the system. So that's what the problem is. So from the point of view of somebody who is a networking developer, the F-trace data, the LTTNG data, and so forth, looks like low-level data. So we have to find a way to present the trace data that we can get from such systems by using all these different methods in a way that is much closer to the needs of somebody who develops networking applications. There's also a set of networking tools, such as Wireshark, for example. Now, these tools, they tell you what happens with the system when the system is seen from outside. Okay, so they'll be able to tell you what is the throughput on a particular interface, or what are some statistics that have been computed by looking at the log of the network packets. But these tools, they don't give you any insight into why you only had 50% of the throughput that you were expecting. So this is why we believe that there is a need for a new type of tools, and that is tools which are focused on the networking data, on the needs of the networking application developers, and also tools that give you insight into what happens with those network packets once they reach the SoC hardware or the software that is running under Linux on the general purpose core of that device. And of course, we know that none of these tools can possibly solve all the problems of those users. Therefore, we have to make them in a way that makes it easy for these tools to be integrated with other tools. These are the main use cases that we are targeting. Oftentimes, those who develop applications for networking, they simply want to trace their packets in the system so that they can confirm that the data flows on the expected paths. Or they want to understand why they're losing packets in the system. The packets may be discarded because there's a QoS, there's a quality of service application, for example. And sometimes that is not clear at all. You simply have no idea why the packets appear to simply be destroyed at some point in the system. And there's also a bunch of other use cases that you can see here on the slides. We want to allow users to measure the networking metrics, such as the throughput or the packet dropout rates. We also want them to be able to measure the latency of processing those packets in the system. And also, we want them, in the case when the system is a multi-core system, we want them to understand very easily how the networking loads are being balanced in the system. So these are the main issues that we have been faced with when developing tools for networking processors. Number one, the software trace, the F-trace, LTTNG trace, and so forth, that is insufficient when a lot of the networking functionality is offloaded to hardware. Okay, the software is simply unaware of that. The other problem is that in these multi-core systems, the data has to be collected from multiple sources. You have to be able to correlate the data in a meaningful way among those sources. And finally, you have to be able to visualize that data in a way that is effective. The other problem is that in the systems, at least in the systems that we have been dealt with, those systems happen to be very complex. And therefore, simply managing the hundreds of trace settings is a non-trivial problem. And finally, you have heard in the presentation from ARM, there is a problem when you try to collect too much trace data. So therefore, you have to be able to control what data you collect and when you collect it. On the next few slides, I'm going to present the work that we did, and we have called this tool the Freescale Packet Analysis Tool. And these concepts that I'm going to discuss here, I think that they apply to other situations as well, not just to Freescale Silicon. Now, our tool, in essence, is a very user-friendly tool that uses the hardware trace from the Freescale devices, and it therefore allows us to collect that trace data in a non-intrusive way or with low intrusiveness. And after we collect the trace data from the devices, we are presenting it in a way that is very packet-centric. In a nutshell, this is what the architecture of the Freescale devices looks like. I'm not going to go into the details. All you have to know is that there is a bunch of cores. There is a system bus, which we call CoreNet, the light blue bar. And there is a central data exchange mechanism, which is called the queue manager. And once the packets arrive from the network, they're being handed off to the various cores in the system or to the hardware accelerators, such as a crypto accelerator, one piece of hardware that knows how to encrypt or decrypt packets. And all of those data exchanges happen via this central data exchange mechanism called the queue manager. So the hardware trace that we use for our tool, what it does is that it is, number one, it's based on something called the IEEE ISDO 5001 Nexus. This is Freescale's hardware trace solution. And what the trace data does is that for every single packet that we trace, we get some information about how that packet was processed while inside the hardware. And that means, for example, if the packet had to be dropped, we do get an indication of that, and also we do get the reason why the packet was dropped. We do get the ID of the trace point. There are multiple points in the system where the data gets collected, where the trace data gets collected, and therefore we have to get an ID, a unique ID for every point in the system from where we can get the trace data. And of course we get timestamps from a hardware clock. Now, the content of the packets, meaning the packet headers and the payload, that does not show in the trace data. I'm going to skip ahead a little bit here and tell you very briefly why this tool is useful. What I have here on this slide is the output of two tools. The top part of the slide contains the output of iPerf, which is this little open source application that you can run to measure the throughput on a network interface. What that tells us is that there's a 25% packet loss. But the tool does not tell us anything about why that happened. And when we use the packet analysis tool, which is on the screenshot here, we get to see very clearly that the packets have been processed on two different processing paths, and I'm going to explain what that means in a few slides. And we can see that 3/4 of the packets have been processed in one way and 1/4 in a different way. So that's a very clear indication that something happened differently for some of the packets. And then we can look at the details in the tool and we can find out exactly why some of the packets have been processed in a different way and therefore ended up being discarded. All right. Let's talk a bit about the specifics of how the trace analysis tools have to be implemented for the networking application developers. As I said, the software trace is insufficient when the users use hardware to accelerate the way that they process the network packets. And therefore, as I said, we do use the hardware trace that is available in the Freescale devices. We can collect this trace data from the central data exchange mechanism. So basically, we get to see every single exchange that happens, which involves these network packets. And this whole thing, this whole trace data collection can happen while the packets are being actively shuffled back and forth among the various subsystems that we have on the chip. And we can do this in a non-intrusive way or with very little intrusiveness. The other thing that I mentioned was that when we deal with a complex system that has multiple cores, it has some specialized hardware that knows how to process the packets and so forth, is that we do have to collect the data from multiple trace sources. We have to correlate the data and we have to visualize it in a way that makes sense. Now, the hardware trace data that we get simply shows us exactly how the various components of the device have touched every single packet that we want to trace. And of course, in the future, when we are going to add some extensions to support software trace for seeing what happens with the packets while inside the software, we'll be able to get similar data from software. This is an interesting topic about what happens once you attempt to correlate the trace data or to synchronize the trace data, as I heard some of you referring to this issue. First of all, there are three different types, at least three different ways that you have to use when you want to correlate the trace data. first of all, these network packets, they live in the system for a while, and they end up being processed by different components of the system. And therefore, you have to be able to understand what happened with one packet while that packet was seen at different points in the system. So I call this correlation between subsystems. Then there's also the issue of identifying the packets that have been processed in a related way. This would be a networking data flow. So for example, all packets that came from the source were sent off to this thread running on this core. Whereas the other packets in the system have been sent to a different thread on a different core. And finally, we simply have the issue of having to correlate or to synchronize the data that has been collected from multiple trace sources. Now, when it comes to how we have dealt with this problem, the answer is pretty straightforward, and that is the hardware trace. We get one trace message, as we call it, for every single packet that we trace. And each of these trace messages contains the address where the packet was stored in the system's memory. And that can be used as a unique ID. And by using this, this unique identifier for the packets, we are able to achieve this correlation of the data that comes from different sources, but which refers to the same exact packets. And finally, when we analyze the trace data, we're able to identify the networking data flows, which we call the processing paths. And on the next slide, I'm going to talk about this a little bit. The term processing path that we use in our tool, that refers to a data flow. And we identify those simply by analyzing the decoded trace data. And on this slide, you get to see an example of such processing paths. These are simply put the sequences in which the packets have been processed in the system. And we show here on the right-hand side multiple such sequences of the packets. Some of them simply went from the networking interface into a core, whereas others went from the network interface to a core and then to a hardware accelerator that knew how to decrypt the packets. And on the next slide, I'll show that you can use this system to understand how the load balancing was achieved in the system. You can see in this example that 60% of the packets went on one path, whereas 40% of the packets went on a different path. So this way, it's very easy to understand what happened with your system at the macro level. If you want to understand what happened with every single component that is involved in each of those so-called processing paths, for example, with the data exchange mechanism, what were the latencies while the data was inside that data exchange mechanism compared with the latencies while the data was being processed by some hardware accelerator, you can do that as well. Finally, if you want to get more details about what happened with the packets, you get to see the trace events basically filtered in this way. The data is grouped for each of the data flows. You get to see the time when a packet was observed, and you get to see the latency, meaning the delta between the consecutive trace events that have to do with the same packet. And also the other thing that we do is we present a lifetime of the packets that we have traced. This is, of course, very straightforward. All right, now, as I said, currently the tool that we have developed only supports hardware trace. But we do want to expand the functionality of the tool, and we do want to support software trace as well, so that we can have comparable features that also apply to what happens with the packets once the packets reach the Linux code. The networking software trace can basically be instrumented to provide data which is very similar to what we get from the hardware trace. And that is, we can still get the frames, meaning the packets, address in the memory. If there's an error that happened while the packet was being processed, we can, of course, get that error code in a stream of trace data. We can get a timestamp and so forth. The software tracers that we have talked about today, you can see all of them here, LTTNG, ftrace, and so forth. But the problem with those is that they can be intrusive. Once again, this has been mentioned several times during this set of presentations. So what we are hoping that we'll be able to do in the future is to use hardware-assisted software trace. You've heard about the core site extensions to Linaro, and we hope that we'll be able to use that as well as the equivalent for the Freescale Nexus hardware trace. The advantage of using this software trace that is leveraging the hardware trace features of the device is that there's a good chance that this is going to be either non-intrusive or it's not going to be as intrusive as the pure software implementation of those instrumentation points. And also, if the hardware trace is able to provide the timestamps, then there's a high chance that those timestamps are going to be very accurate and very easy to correlate with the timestamps for other trace data that you're going to get from the device. When it comes to correlating the software trace that we are going to get, we have the same three issues, and that is, how do we correlate the trace data that has to do with the same exact packet when that packet ends up being processed in different places? We have the issue of how do we recognize the data flows? And finally, how do we simply correlate the different logs, the different sets of trace data that we collect from multiple sources? For the first one, between correlating the packets between subsystems, we can simply use that unique packet identifier that I have mentioned before. For example, the address where the packet is stored in the system's memory, assuming that that doesn't change. For the data flow identification, meaning to understand exactly how is the system sending packets on the same paths, let's say from this software procedure into this other software procedure and then eventually into some hardware accelerator, we can do the same thing that we did in the case of the hardware trace. And that is, we can analyze the trace data and we get to automatically determine what are the processing paths that the system has used. And when it comes to correlating the trace data that we get from the different trace sources, some of you have used the term synchronization for this. This is typically done based on the timestamps, but in that situation, the problem is that those timestamps may come from different clocks, and therefore, and also those clocks may run at different speeds. So you may have to do some, or our tools may have to do some correlation, some adjustments to make sure that those timestamp values do indeed match. And finally, if the timestamp correlation is not possible for whatever reason, there is also the possibility of correlating based on trace annotations, on markers that exist in multiple sets of trace data. And on the next slide, I think I have an example for that. This is how we have correlated some hardware trace that we have collected with our tool with the packet logs that Wireshark has collected. The idea was very simple. We have injected some ICMP packet markers in the trace, and we have used different sizes for the first packet, the one that showed up at the beginning of the test, and for the last packet. And once we did that, we were able to see in the two sets of trace data, the background contains the Wireshark view of the packet log, And the other two screenshots contain the views of our tool, of the packet analysis tool. So we were able to match the entries from these two logs, and then based on that, we were able to determine the ranges of the two sets of trace data that were actually referring to the same exact packets. And then, of course, once we had that, we were able to also correlate the statistics, which were computed by Wireshark, which is the top screenshot, the one at the bottom, and also the statistics that the packet analysis tool had computed. All right, in terms of what we want to do next, as I said, we do want to provide, with the packet analysis tool, we do want to provide visibility into software. And I think that this is the part where we can work with the community to define exactly how that can happen and how we can benefit from a collaboration. We also want to use the software tracing that is based on hardware capabilities. For example, the Linaro core site. And finally, we want to focus the analysis of the data on the interface between the software and the hardware. A lot of times, most software developers, they're not willing or able to reconfigure the hardware. So they simply stop at, let's say, at the driver level. So we do want to be able to provide good support for analysis at that level. And in terms of correlating and visualizing the trace data, we are considering using the common trace format and also the Trace Compass project so that we can easily correlate the hardware trace data with the various types of software trace data and with the packet logs. And in conclusion, we went over the specifics of developing tools for the needs of the network application developers. The packet trace does provide unique insight. It allows people to see what happens inside the software, and also it allows for doing analysis at the macro level. If you have more information about the tool that we have developed, just go to freescale.com and search for packet analysis, please. So let's see if you have any questions.
Thank you, Petru.
Sure. Yeah?
Can we get quickly to the problem which is quite close to my heart, which is the time-step correlation?
Sure.
The markers, that's the obvious solution. You've got a set timestamps for the same event from different sources. Then you just do linear correlation.
Right.
But you've also mentioned some other magical timestamp correlation and normalization may be required. And if you've touched that, you may have some other solutions. Have you tried anything like the statistical analysis and just finding peaks and trying to correlate them automatically without the markers? Let's assume you have no markers, right?
Correct.
So you don't have the points of well-known points with timestamps from different sources. Have you got any idea how to actually correlate it without it?
Currently, no. To be honest, I was counting on the ability of using the timestamps to achieve the correlation. But this is a good point. It is possible that we simply don't get those timestamps, or that we don't know how to correlate them. So that's a possibility. Looking for peaks in the stream of trace data, that's an interesting idea. I haven't thought a bit about it, but.
Other question? So can you go back on, I think it was your last slide, or the one before your last slide? You were mentioning about the network analysis. Yeah, this one. So I guess you know, but in Trace Compass, all of those things are working today.
Yes.
With PCAP and so.
Okay. Right. We hope that we'll be able to leverage what already exists in Trace Compass and add support for the hardware trace, for example. and see if we can, that way we can give a more comprehensive image of what happened with the system.
Okay, maybe one last question before we start the panel? No? Okay, so thank you, Petru.
Thank you.